Welcome back to Hoffman Tactical. Okay, so today I'm going to be doing some filament testing, but first I just want to mention that you'll probably notice I haven't put a video up in a couple weeks. That's actually because last week, a little over a week ago, one of our videos got removed. Again, this is the second video I've had that's been removed by YouTube for violating their terms of service, and as far as I know this video didn't, but they removed it. Our appeal was turned down and I couldn't upload anything for a week. They locked my channel, so that's why there was a delay. And I had got my account out on Odyssey.com set up, so I looked at a bunch of different alternative platforms and I finally decided for at least for now to go with Odyssey as the primary alternative platform to YouTube. So definitely head out there, create an account with Odyssey. It's a good platform, it's a solid platform. All of my videos which are on YouTube currently and that I have uploaded to YouTube, like this video for example, will be out on Odyssey, so you can watch all of my videos out there and never have to come over to YouTube. So definitely go out there, because obviously my days at YouTube are numbered, so at some point we're going to be removed completely from YouTube, and the alternative platforms will be the only platforms to have videos on. So definitely head out to Odyssey.com and check out my alternative channel out there. Okay, let's jump into this filament testing. So today we're going to be testing 3D 870 PLA, and that's like a high temperature PLA plus, and I'm just picking that because I like the filament, it's easy to print with. This is the first test that I've done with my new testing method, so we're going to be testing both the impact resistance and the tensile strength of this plastic with different print orientations, and I'm going to try to do a little bit of high temperature testing to see how it deals with elevated temperature conditions. So I'm going to do that a little differently than most people do it, so that's kind of experimental, so we'll see how that goes. Okay, so here are our test samples. So we have right here, these samples are for the impact tester, and these ones are obviously printed vertically with a brim. And these samples are designed to be broken off in the impact tester right here, and that is going to test the impact resistance. These ones here are the same sample as those, but these ones are printed flat with all of the lines orientated this way. So this is going to be testing the actual material strength, and this one's going to be testing the layer adhesion of that material with my particular print settings, the print settings you use will vary the layer adhesion by a lot. It's another subject for another video. So you got to take any layer adhesion testing with a grain of salt, but it should give you at least some idea of the ability of that plastic to adhere with the layers. And it'll kind of show you the difference between vertical printed parts and horizontal printed parts in general for 3D printing as far as their mechanical properties. Over here we have our vertical tensile test samples, and these will go in the tensile test machine right there. And we're going to break those very slowly, so will be no impact loading, and we're going to see what the tensile strength of this plastic is, both printed vertically, so the layers run this way, so that this is going to be a layer adhesion test, and horizontally, and the horizontal test sample is going to have all the layer lines running this way, so that we're testing the actual material strength without any layer adhesion getting into the mix. So this is going to give us our actual material strength, our actual material impact strength, and then these guys right here are going to give us the ability of the material to have layer adhesion, what the layer adhesion of the material is between different lines on that material. Okay, so right here you'll see we have some extra test samples. What we're going to do with these guys is I'm going to load it into the impact tester, the tensile tester. I'm actually printing some more impact ones for this as well. I'm going to heat it up to a certain temperature, probably like 140 degrees Fahrenheit, and then I'm going to test it with the same process I use to test the ones at room temperature, and we're going to see how room temperature compares to the standard samples. Okay, so before we start breaking samples, let me give you guys a little background into my testing process. So the very first thing I do is I print a little calibration cube. It's more of a square, a flattened cube, and I use that to calibrate my flow or my extrusion multiplier, and that is to make sure that the nozzle is extruding enough plastic to properly fill all the gaps when I'm using 100% rectilinear infill. And that is really important for doing accurate layer adhesion tests, because if it's under extruded even a tiny bit, it'll dramatically affect your layer adhesion by like 10-20%, depending how much it's actually under extruded. So I do that, I print that piece first to make sure I get a properly filled infill. I have enough plastic extruded out. So my extrusion factor for this test came out to be 4% over the standard extrusion amount, so 1.04 was my extrusion multiplier. The next test I do is I print a bunch of these vertical test samples at different temperatures, different nozzle temperatures, and I'm trying to find the optimal temperature for whatever plastic I'm testing. So with this plastic here, the optimal temperature was right about 250 degrees Celsius for the nozzle. And above that, it starts going back down, you start losing strength. Below that, it dramatically drops off down. So I tested from 200 to 260, and you get a lot of gain in strength up until about 250, and then you drop off again afterwards, going back down the other side. I assume because the material is degrading because of the high temperature, for whatever reason. But I do that in order to find the optimal temperature for printing whatever material I'm testing. And then after that, I actually start on the real test. And the reason I do those two initial tests is because I want to actually test the material's properties in the best light of that material. So if I'm testing this material with the wrong print settings, I'm not going to actually understand what the material is doing. It's my print settings that are making it weaker. So that's why I do the temperature and the extrusion multiplier tests first, so that my layer adhesion tests later are more accurate. And we'll start this test with the fun part, which is going to be the impact tester, and we will start with the horizontal test samples because these are going to be the most difficult ones to break. I actually have not tested the impact tester in its current configuration with this new style of test sample, so we're actually not sure if it's going to work or not. Let's find out. Okay, before I actually break the first sample, I'm going to do a test run to see if the tester is actually working. Everything looks like it's in place. I have the computer, the serial monitor running, and it says that the absorbed energy was 5/100ths of a foot-pound. So that's almost zero. That's because there was no absorbed energy because there was no sample there. So I'm going to lift it back up. The machine is ready. Now we're ready to break the sample. So we just load our sample into the machine. There's actually some little spots in here that snap onto this hole. So it just goes in here. This needs a little work, but just presses in, and a little too far that time. Yeah, there we go, snaps into place, so it's always in the same place every time. As you can see, it's a little bit loose. That shouldn't affect it. I always push it to the bottom, so that it's the same every time, but we'll see. Okay, let's actually break this part and see what happens. Ready, set, go. 4.5 foot-pounds. We're gonna take our official sample remover right here, and just press the sample out from this side, like so. So you can see our sample broke off at the notch like it was supposed to, and it absorbed 4.5 foot-pounds. Let's break the other two and see if we get consistent results. 4.23. Alright, you guys can clearly see here that our three samples absorbed 4.49, 4.23, and 4.5 foot-pounds. That's pretty consistent if you ask me. We'll take the average of those. Not sure why that one was less. The sample looks the same after it broke. And the only concerning thing here to me is that this is 4.5 foot-pounds. My machine can only deliver 6.5 foot-pounds. So we've only got a couple extra foot-pounds. If we get some super tough material that can absorb a lot of impact, I'm going to need to increase the oomph of my machine over here to actually be able to measure that. Okay, so here we can see that the break is actually really clean on these parts. It actually looks pretty good. The infill is pretty solid. There's no really voids in there, and they all look pretty much the same. I'm not really, this one here might look a tiny bit different. Let me focus on that for you. They all look pretty much the same, so pretty consistent results. I'm pretty pleased with the results, and our samples look properly extruded, so I would say these numbers are accurate and we can move forward with our test. So these samples were a lot weaker than the other one. They only absorbed about a foot-pound of energy, and they broke off completely without leaving anything behind. Yeah, you can see the results there. Also relatively consistent, not quite as consistent as the horizontal test samples, but we only absorbed about, and yes, I am touching the screen. It doesn't really hurt it. It's good for the video. 1.06 foot-pounds, 1.11, and 1.27 foot-pounds, so like a quarter the strength of the impact resistance of the vertical test sample, but still actually not horrible. All those samples broke around 260 pounds, 250 pounds. I still have to calculate the PSI, but it was kind of interesting because two of the samples, the two later ones, failed with a bit of plastic deformation, as you can see there, and it kind of stressed before actually this one's still connected. The first one we did, on the other hand, just snapped apart and broke, which is kind of interesting. So that I'm assuming maybe my hands warm this one up slightly, though I am really careful to only ever touch the ends of the sample because your fingers will warm the sample up to like 90 degrees above room temperature, and that will give you a inconsistent result. The consistency is important. So that was kind of interesting, but the actual amount of force it took to actually get the sample to yield in the end, whether it yielded plastically or whether it yielded suddenly, was the same, around 260 pounds. So the results should be consistent, but still kind of interesting. Okay, just taking a quick look here, you can see that we were actually 8,577 PSI average, which is really good. The results were super consistent right there. Super consistent, and that is what our graph looks like. So the first sample we tested yielded pretty suddenly, the other ones yielded in a plastic way. So all in all, this is kind of a rough, crude stress strain curve. The machine stretches and stuff, so it's not accurate, but we'll go with it. So you can see quite consistent results, 8,500 PSI. Now let's test the vertical test samples and see how they do. I'm guessing they're going to do quite more poorly. And also will not have any of this plastic deformation. Those all break suddenly. That's my guess. Okay, so here are the results of the vertical tensile tests, and as you can see, we came in at like 5,500 PSI, and we were pretty consistent. Those is actually very consistent, so pretty pleased with the consistency, especially for vertical tests. Layer adhesion tends to not be as consistent as horizontal tests. So the tensile strength is 5,500, which is really good for a vertical tensile test, so that's pretty good layer adhesion. And then looking at the graph here, you can see there was actually a little bit of plastic deformation right there at the end, which is kind of interesting. It was kind of starting to yield a little bit before snapping, which I had not seen before with tensile tests, but I did go through extra measures to make sure I was getting the best layer adhesion. So there was no fan, for an example, on this print. So after that, you can see that we did suddenly fail in the end, as you can see in the videos of the parts breaking. So it is still pretty brittle, and that brittleness showed up in the impact test because it didn't rate too well in the impact test. There's one test I have not done yet, and that is the temperature resistance of this filament, of this plastic. So how hot can you go before it gets too soft to actually function? And this test is going to involve a hot air gun and a very accurate thermometer. So normally this kind of test is conducted by taking a sample of the plastic, putting it across two supports on each end. So it's supported on each end, but it's like a bridge basically. And then you put a weight in the middle, then you heat it up gradually in like an oven, an accurate oven of some kind, until it begins to droop. And that tells you what is it's called the heat deflection temperature. And that's useful for comparison purposes. But I actually don't have a super accurate oven or setup like that, but I do have these items here. So I'm going to attempt to do, this is strictly experimental right now, but I'm going to load one of the some samples into the tensile test machine. I'm going to use the hot air gun and this thing here, and I'm going to change the distance of the hot air gun so that the sample is warmed up to a certain temperature. I'm going to shoot for like 140 degrees Fahrenheit. I'm going to give it like 10 seconds to heat up to that temperature, and then I'm going to run the machine and see how the polymer performs at the elevated temperature. And I used to use these used to be my jaws for holding the sample. The ball hold, these are actually sockets. So these are the socket holders for the samples. These are made from a PLA, which was really, really strong, but unfortunately not temperature resistant. So I reprinted the samples from a polycarbonate blend, which should be able to easily go up to 200 degrees Fahrenheit. So that should let us test plastics at around 150 degrees Fahrenheit without damaging the machine. Hopefully. Let's find out. Okay, if I hold it right here, it looks like we can get, I just misaligned it, line it back up. I can get 100 and, that's 132, 125, 134, 135. There we go, 150 if I hold it right there. Hold it right there, and we get, well, keep it lined up, 150 degrees Fahrenheit. All right, it's 10 seconds, and we're at 155. I think that's long enough, and I'm going to hit enter. Okay, our sample is pulling. 159, 150. Okay, I'm going to keep blowing at it. See what it does. $146, and we're popping through. It's 159. It only took 24 pounds of force to do that. That's it, 24 pounds. There's our test sample after the test, and as you can see, that end is pretty deformed. It took almost no force to do this. It just stretched it out. It was pretty soft. It began to kind of yield right here at the neck part. So what kind of happened here was I had the hot air gun blowing on it. You can see this end isn't deformed at all. This end is really deformed. So what happened was it's just a focused amount of heat blowing on that sample there that I had the thermocouple a little bit too low, and it was actually like 160 degrees Fahrenheit up here, and that's what actually stretched it. So the problem is getting an even temperature all across the sample with a hot air gun isn't going to be really easy. But as you can see, the temperature resistance of this stuff isn't the best. So that was pretty hot. That's pretty high temperatures. It's hotter than you're going to find in your car, for an example. But this test is going to need more work because obviously that result is not going to be consistent because the sample was not heated evenly. Now if I could find a way of integrating my filament dryer, now that would be interesting because this thing is pretty consistent. Okay, so here I'm just quickly looking at the results in our spreadsheet. This is the tensile strength, and you can see that the vertical test sample with layer adhesion was actually more than 50% the strength by quite a bit. It was 5,500 compared to 8,500 PSI tensile strength, and so that was actually pretty good. Now, so just looking at these results aren't very helpful without being able to compare them with other filaments. So I'll be doing more testing, and then we can compare it, and it'll be more useful. Scrolling up real quick to the impact test, as you can see here, the big difference was with the impact test. The vertical test samples did very poorly compared to the horizontal test samples, and I want to just touch on something here real quick, and that is units. So down here, whenever I do any impact testing, I'm doing units in pounds per square inch. So this, I'm calculating the the cross section of this sample right here, and then I am computing how many pounds it would take to break an equivalent sample that was 1 square inch in cross section. So a 1 inch by 1 inch square would take 8,500 pounds was printed horizontally to actually break, in theory, calculating. So that's what the units is for tensile strength. The units for impact strength are a little bit less well defined. So these units are foot-pounds of energy absorbed. The convention is to use a unit like foot-pounds per square inch. So kind of like tensile strength per square inch, you would use foot-pounds per square inch or even foot-pounds per linear inch of the height of the test sample. Unfortunately, I find those to be very, very subjective numbers. It really depends a lot on the shape of your test sample and exactly how it was hit. So I think defining it that way isn't really accurate. So instead, I'm just going to stick with foot-pounds of energy to break the specific test samples I am using. And while that won't be helpful to compare to other people's tests, it will be very helpful for comparison purposes between different plastics on tests that I do. So these units for impact tests will always be in foot-pounds of energy that specific sample absorbed, with no other units attached, just foot-pounds. So that kind of explains the units. Those are our results. Okay, I hope you guys found today's video interesting. It wasn't so much to show you the results of the test, because as I said, having just these results isn't very helpful without being able to compare them to other plastics and see which one is best, which one is strongest, which one's more impact resistant. This was more to show you guys the process I'm going to use to test plastics, and I'm hoping it's going to give me consistent, accurate results. I've been working this for a few weeks now, trying to ensure super consistent results and make sure I don't have any parts of my test, of my process, that's going to give me errors or give me false results that are going to lead me to the wrong conclusions. So I'm going to be doing more testing right now. The next plastics I'm going to be testing are going to be nylons. I have some Matter Hackers nylon as well as alloy 3D. I have alloy 910, and then I bought some carbon fiber nylon from Push Plastic, and I'm going to see how that is. So I'm going to do a big test. I'll probably test the 3 Matter Hackers nylons first, see if the glass fiber, the carbon fibers, the plain nylon, which one's more impact resistant, which one's stronger. That should be interesting. So stay tuned for that. And as I said at the beginning of the video, head out to odyssey.com. I'll put the link up here so you guys can see it. I'll just print it on the screen. You guys can type it in. Head out there. If you've stuck to the end of the video, you probably watch our videos, probably interested in them. So at some point, YouTube's going to cut us off. So head out to Odyssey. Get an account out there, subscribe to my channel out there. As I said, all my videos that go on YouTube will be out on Odyssey, so you can watch everything out there. You won't miss anything. So head out there, watch my videos on Odyssey, and I'll see you guys again in the next video we do. Thanks for watching.